Hiya and welcome to day 15 of the 24-day extravaganza. We're only about almost 10 days to go here, and I've got a question that's more of a A-level question, and it's dealing with simple harmonic motion. So what I've got here is, I'll explain why I know it's simple harmonic motion too, is our student is investigating forced vertical oscillations. And if you see that term oscillations in springs, it means you are dealing with simple harmonic motion. Two springs A and B are suspended from a horizontal metal rod that is attached to a vibration generator. The stiffness of A is K. So this has got a stiffness of K, and this has got a space of 3K there. Okay. The vibration generator is connected to a SIGGEN. SIGGEN is used to vary the frequency of the vibration of the metal rod. So it's forcing the objects to oscillate. When the signal generator is at 2 Hertz, the mass A oscillates with a maximum amplitude. So we are at a maximum amplitude, we are at a resonant frequency, okay? And this is 2.5 times 10 to the minus 2. It has a maximum kinetic energy of 5 or 54 millijoules, okay? So deduce the spring constant and mass of A, okay? So we are dealing with simple harmonic motion of a spring. So what I start to do is I will put all the formula that I know. So I know that, of course, T equals 2 pi square root m over k. Now this is a bit of a problem because, of course, I've got m and k in here. I've been given the kinetic energy, which is a half mv squared, okay? And since we're dealing with things moving, I also know that Vmax equals omega A, and omega, of course, equals 2 pi f there. So there are many ways to do this, and I'll show them on screen in a bit because there are a few methods to do this, but I'll show you the method I would do. Is that, okay, I know the kinetic energy, I can work out the maximum velocity because the maximum velocity will give me the maximum kinetic energy. So Vmax equals omega, so that's 2 pi f, so 2 pi times by 2, oops, t, 2, not t, oh. Okay, 2 pi times by 2 is omega, times by my amplitude, which is 2.5 times 10 to the minus 2 there. So I can get my value for my maximum velocity. So 2 times pi times 2.5 times 10 to the minus 2, and I get a maximum velocity of 0.1, 2 times by 2, 0.314 meters per second, okay? So I now know my kinetic energy, my maximum kinetic energy was 54 times 10 to the minus 3, and that's going to be a half times m times the maximum velocity, which is 314 squared. So I'm going to square that. I'm going to have 54 times 10 to the minus 3 divided by that. And then I'm going to times that by 2, and I get an answer of my mass is 1.1 kilograms. I can then use this formula here to work out the spring constant of this object here. So T equals 2 pi root m over k. So T, of course, if it's 2 Hertz, T equals 1 over the frequency, so that's 0.5. So what I have here is I have 0.5 equals 2 pi root m over k, where I know that m is 1.1. Okay, so putting that into my thing, so I've got 0.5 divided by 2, so 0.5 divided by 2 divided by pi. I square that, and I have 6.33 times 10 to the minus 3 equals m over k. So k equals 1.1 divided by that there. Okay, I've got k equaling 173.7 newtons per meter. So what you have here is I've got my mass, my spring constant is 173.7, and my mass is 1.1. So really important, if they give you lines where you've got to put your answer, please make it clear that that is your answer there. Now I'm going to show you the mark schemes, so you can actually see there are numerous ways to solve this one. So this is the method I used. So this is the method I used where I worked out my velocity, use that, find M, and then use the formula. You could have also used that you knew that when, if you knew the energy, maximum kinetic energy, that you know that's also the maximum strain energy, so a half Fx or a half Kx squared. So you could do that information there. Or they were looking at F equals Kx as well. So there's numerous methods you could use to work that out. But in essence, you would get 1 mark for each of the answers and 1 mark for the method of each of your answers as well for 4. Calculate the frequency at which the mass with the spring attached to B would oscillate with a maximum amplitude. So you basically, it's just using the form here. So you know that B has 3 times by K. So B's spring constant is going to be that times by 3. So it's going to be 521 newtons per meter. Okay, you know it's got equal. So if I go back up to here, it says equal masses. So it's also got a mass hanging from it of 1.1. So you can find the time period. So T equals 2 pi root m over k. You can find its the time period for its natural frequency. So I've got 1.1 divided by that. I've got to square root that answer and times that by 2 and then times that by pi. And I get an answer of my time period is 0.288. And my frequency, of course, is 1 over the time period. So my answer is 3.46 hertz. Okay. Double check my answers on my mark scheme. And what we've got here is 3.5. So there we go. That is how you can manipulate this data. So it is it's simple harmonic motion. I tend to write all the formulae for simple harmonic motion down. I knew it was simple harmonic motion because it said oscillation. So here you got 1 mark for the method and 1 mark for here. You do get error carried forward whatever you calculated as your K. So when you have simple harmonic motion, damping and resonance is one of the important parts of it. We kind of mentioned resonance before, but this is what's happening here. Figure 2 shows how the amplitude of the oscillations of the mass varies with frequency for A. The investigation is repeated with B, but B is also immersed in a beaker of oil. So the graph will vary, the variation of the amplitude thing is different. Explain 2 differences, okay? So if you think about it, the natural frequency of B is actually going to be 3.6 or 3.46. So I know that if this was without the oil, I know that I would have a peak here, okay? So I would have a peak to the right of the object. So the difference, one, of course, is that spring B, so it's explained, spring B will have a peak to the right because, and this is an explained question, because the natural frequency is higher than 2. Okay, so its natural frequency, its peak, will be to the right at 3.46. Okay. The second difference, of course, is it's going through oil. So it has been damped. So what happens to these graphs when it has been damped? The amplitude would be lower. So the amplitude would be lower, the peak amplitude would be lower because the system, the spring, has been damped. So spring B will have a peak to the right because the natural frequency is higher than 2. And the peak of the amplitude would be lower because the spring has been damped. Grabbing the mark scheme here. So to any 2 from, so you actually get a mark for saying what the difference is and then a mark for describing why. So the peak would be at a higher frequency due to a higher spring constant. Okay. I mentioned it would have a higher frequency because it's natural. So the peak would be because it has a high frequency due to it has a highest different natural frequency. And then the amplitude, so here, this is what I said, the peak would be broader due to damping, or the amplitude would be lower due to energy losses. Okay, so I'm mentioning about that damping there. Okay, so that there is a nice question here. Explain two differences. As per usual, we get one will one for saying what the difference is. So the spring, the peak would be to the right, or the amplitude would be lower, and then the explaining part, the because afterwards, you would get this second mark for. So there we have it. That's the first of our sort of second year questions here. This is more of what would be on a paper. It would be on paper 1, but it is more a second year content. So there we have it. That is day 15 of the 24-day extravaganza.